Greetings, aspiring scientists. Welcome to my video today on Introduction to Organic Chemistry. Here I am at school again with my doppelganger, Detective Conan. I didn't draw that, but one of my coworkers did. My class recently graduated here in Japan, so I'm pretty free. Decided to make a video today. So let's get into my slides. And for the periodic table section that I finished last week, we didn't go over the guiding question, so let's start with that. So the question was, how does the periodic table help us predict patterns and trends in the properties of elements? So the periodic table was basically arranged first based on atomic mass and then atomic number, and it was decided to start and stop the periods and rows at certain locations based on what we now know is electron configurations. But doing that sets it up so that there are specific trends in electronegativity, radius, whatever else we talked about, electron affinity, ionization energy, and so on. And so just by moving around the table that we set up in that way, we can notice trends and predict changes in those characters and numbers. So we're finally in structure 3.2. This is the last section of structure 3. Not only that, it's the last section of structure in SL chemistry. So once we're done this, we're going to be sort of done talking about how molecules and atoms exist and more focus on reactions. The next section is reactivity, the second half of the course. But for today, we're doing classification of matter functional groups in the classification of organic compounds. So I'm going to introduce what organic compounds are, and we're mainly interested in their structure, properties, naming in this structure section, and less about reactions and reactivity. But you will have to know all that stuff in the end. So our guiding question for organic chemistry: how does the classification of organic molecules help us to predict their properties? So again, we're talking about classification, grouping, naming, and then their properties and how we can predict that from their classification. So the first section that I'm doing today is 3.2.1, formulas of organic compounds. And along with this, I'm just going to introduce what organic compounds are and what organic means. So some vocabulary to do with organic chemistry. What is an organic molecule? This is a molecule that is primarily based on carbon and hydrogen atoms. And sometimes the line is not so clear, but definitely if there's no carbon, it's not an organic molecule. Something like CH4, methane, is organic, carbon and hydrogen based. CH2O is also organic, even though it's got an oxygen, and the oxygen is actually a very significant part of this molecule's weight. CH2O is still organic, but CO2 is not, no hydrogens, just two oxygens. So you kind of need carbon and hydrogen, I think, at least one of each, maybe that's the rule. Then we come to this idea of catenation. Catenation is the ability of atoms to form chains, branch structures, and cyclic molecules. Okay, and this is heavily a property of carbon atoms. We've studied, molecular geometry previously in my videos and in this course. So we know carbon atoms tend to be tetrahedral. They tend to form 4 bonds with angles 109.5 degrees away from each other. That structure allows carbon to form many bonds, long chains, branching chains, and ring structures, which is really important. It leads to a wide variety of three-dimensional structures. So homologous series. This is a series of organic molecules which differ only by their carbon chain length. So we'll get into what that means later, but it just means you can have a particular type of organic molecule, and then you can just extend it by adding more carbons, And if you do that, we say that all of those belong to the same homologous series. They have similar chemical properties. It's just different molecular weights will eventually lead to some physical differences. Hydrocarbon then. Very good to know this word. This is what it sounds like, hydro plus carbon. It's a compound that contains only carbon and hydrogen. So in my list above there, CH4 is a hydrocarbon, but the other two are not because they contain oxygen. Okay, and last, I just want to say, in casual language, you'll often hear people talk about organic things, and what they usually mean is natural, like just grew in nature without human synthetic compounds or some sort of bioengineering, I don't know. But what it means here in chemistry is just the carbon-hydrogen-based molecules. And I also want to say this is my favorite topic. I've mentioned it before, but this is what I've studied the most. This is what I enjoy the most. So I know a lot of details, probably more than other teachers, about these things that I might throw in once in a while. So let's visualize catenation a little bit. What it means first is that we can form long linear chains. For example, pentane, this is 5 carbons in a row with all the extra bonding locations filled with hydrogens. C5H12, it's an N-alkane, is the name of its sort of class. But we can also have branch chains. So instead of just being a straight chain, we can have something like isobutane. It's got a sort of 3 carbon chain on top and then a 1 branch chain coming down off the bottom, C4H10. And we call that a tertiary carbon center because that carbon in the center is bonded to 3 other carbons. We'll get into that naming system later. Cyclohexane then, this is what it sounds like. It's a cyclic molecule, cyclohexane. We've got 6 carbons in a ring. This is a cycloalkane, C6H12. We say that it's saturated. It has basically as many hydrogens attached as possible. They're not replaced with any sort of oxygens or nitrogens or double bonds, triple bonds. It's just got the max number of hydrogens. And we can say that for any chain, it doesn't have to be cyclic. And then benzene is a special type of cyclic structure. You can see this one does have double bonds. This is not a saturated structure because of these double bonds. And with this alternating structure, double, single, double, single, double around the ring shape, we call this aromatic hydrocarbon. And although both benzene and cyclohexane look like hexagons on this, there's actually significant differences between them. We know that the carbons in benzene would be sp2 hybridized. That means that this is trigonoplanar and flat kind of structure, whereas cyclohexane, those carbons are still tetrahedral. So even though I've drawn it as a hexagon here, it's actually often folded slightly into kind of like a lawn chair shape or a boat shape. We might talk about that later, more in HL, I think. These are just 2-dimensional representations of organic molecules and some catenation properties. So empirical formula versus molecular formula. We've talked about this way back in like topic 1, unit 1 in moles, but let's bring this slide back here. We've got some different compounds: butane, water, hydrazine, hexanoic acid, and glucose. We've got their molecular formula and their empirical formula. Remember that the empirical formula is sort of the lowest common factor of the molecular formula. So C4H10, you can divide that by 2. Is that organic though? Yes, it's mostly carbon and hydrogen based. Water, H2O, the molecular formula is the same as the empirical formula. You can't divide one oxygen by any whole number, so H2O. Is that organic? No carbon in there. Hydrazine, N2H4, you can divide that by 2 to get the empirical formula NH2. Is that organic? No. It has nitrogen, not carbon though. Then hexanoic acid, C6H12O2. you can divide that by 2 to get C3H6O. Is that organic? Yes, it's mostly carbon and hydrogen based. It's got multiple carbons and hydrogens. Glucose then, C6H12O6. This is sort of one of the most widely used examples of an organic molecule. It's the fuel that most living organisms use. They'll combust this and break it down, digest it to get energy. But the empirical formula of this, you can divide it by 6, you get CH2O. This is an organic molecule, mostly carbon and hydrogen based. So I'll just draw here, butane, organic for sure. Water, no carbon. Hydrazine, no carbon. Hexanoic acid, yes. Glucose, yes. Okay, I just want to focus on glucose for a second. As I said, it's one of the most widely used examples of an organic molecule because it is the fuel of most living organisms, but it's a good example of what I've talked about. You've got chains, branches, rings in this C6H12O6. So these little white balls are hydrogen, yellowish ones are carbon, blue are oxygen. And it has a main ring structure in the middle. As I said, it's not a perfect hexagon usually. It's sort of this kind of folded boat shape with one side up and then the side across also kind of peaking or pointing upwards. And then just a bunch of little branches of oxygens and hydrogens coming off there. We've also got what we call different functional groups in this. Some of them are OH groups attached. Some of them are COC connector kind of groups. Hugely important molecule for biology as well. All right. So how do we draw and describe organic structures? It's really important. It's one of the things that we're going to be focusing on in this section. So there's different kinds of formula. There is the structural formula, where you would kind of just draw a Lewis structure. Although we often don't draw lone pairs in organic Lewis structures unless they're needed for something. But we can just have carbons with their 4 bonds, hydrogens with their single bonds, and we draw all of them. You could also draw them with their expected angles, like tetrahedral angles around 109.5, but oftentimes we'll just draw them as right angles like this to draw them quickly. So here would be butane, 1, 2, 3, 4 carbons, and 10 hydrogens just attached in every location. So every atom and every bond in the molecule explicitly is written. Each element is written as its symbol. Lines represent bonds. So this format leaves pretty much nothing to the imagination other than angles and 3D structures, but it's nearly the most complete 2D representation. But it's also time consuming, right? You don't want to draw this every time for something like glucose. Condensed structural then, this is a little bit more compact. It could even be more compact than what I've drawn here. You don't even have to draw any bonds at all in the condensed structural formula. But this is nice, it kind of fits in a line. You could, write this in a Microsoft Word text line. That's a good point about it. So groups of hydrogen atoms, along with their parent carbon, writing them as one line, like CH2 or CH3 or CH, etc. Bond lines between carbons are sometimes kept or sometimes omitted. This is a nice practical middle ground. You can draw it pretty quickly, but it does contain all the information of all the atoms. Then the skeletal formula. Although this one requires some practice and learning, I think everyone who goes on to study chemistry will really appreciate the skeletal formula notation because you can draw things really quickly, and if you're in a room full of chemists, everybody will know what you're drawing. So this is the most abbreviated form. Carbon atoms are implied at each vertex, each corner of a sort of zigzag chain. Hydrogen atoms bonded to carbon are omitted entirely. We don't draw them, and we have to understand that wherever carbon doesn't have its usual 4 bonds, there are hydrogens there attached. Only functional groups and heteroatoms, for example, O, N, S, whatever. Those are the other atoms that are not part of the organic nature of C and H. They're called the heteroatoms. Those are usually explicitly written. And if there's hydrogens attached to those will also be explicitly written. This is used universally by professional chemists for speed and clarity. It has the least detail, but it's the easiest to draw quickly. All right, so let's look at some examples of common organic molecules that use these formula. So propane, 3 carbons. You can draw the condensed structural formula, CH3, CH2, CH3, or the skeletal formula, just zigzag. 2 lines. Each of those corners is a carbon. Those carbons have hydrogens attached wherever there is no solid line. So the 2 on each side have CH3. The one in the middle is CH2. Okay, next, propan 2-ol, CH3, CHOH, CH3. So it has this OH group attached to the central carbon. And the skeletal formula, zigzag with an OH attached to the middle. So now that carbon, we understand, has only 1 hydrogen attached because another thing has been labeled, the heteroatom in the OH group. Then next, propanal, CH3, CH2, CHO. And the skeletal formula is like a zig, zag, zig again, but this time a double bond to an O, which is labeled explicitly. So 3 carbons, 1 oxygen. Propanone then next, CH3, CO, CH3. This has a C double bond O in the center. So a zigzag with double bond to O on the central carbon. Now that carbon has no extra hydrogens attached because it has 4 bonds explicitly labeled. Okay, and then last, propene, CH2 double bond, CH, CH3. So I've drawn sort of kind of different angles of this. The double bonds on the right in the full structural formula and on the left in the condensed structural formula. That doesn't matter, you can flip it around, rotate it around, they mean the same thing. But the skeletal formula is like a zigzag with a double bond in between 2 of them on the edge. So in that skeletal formula, the left carbon has only 1 bond. That means it has 3 hydrogens attached. Central one has 1, 2, 3 bonds total, so it has 1 hydrogen attached. And the one on the right has 2 bonds, so it has 2 hydrogens attached. So you should definitely learn how to read and draw all 3 of these types of structures. Definitely practice, because sometimes there are IB test questions that just say, draw the full formula, condensed formula, structural formula. You have to know each one. So a little bit of practice. 1, draw the structural and skeletal formula for the following compounds. So that you should assume means the full structural formula. So butan 1-ol, CH3, CH2, CH2, CH2OH. So I'll draw the skeletal first, just so I know what I'm working with. 1, 2, 3, 4. And you do draw another line here with an OH group. Okay, so this represents 4 carbons, there's 4 corners, and then an OH group attached. Now the full structural formula for this is going to take up quite a bit of space, but C, 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 4 in a row, then an OH on the end, and then every other position around carbons just has hydrogens. So 2 there, 2 there, 2 there, 2 there, and then 3 on the last one. It has to complete the chain and have its complete octet, 4 bonds. All right, B, hexane, 6 carbons in a row then. CH3, CH2, 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 CH3. 1, 2, 3, 4, 5, 6. It will look like this zigzag chain with 6 corners. Then the full structural formula for this. We'll just draw 6 carbons in a row. 1, 2, 3, 4, 5, 6. 3 hydrogens on the ends of this chain, carbons. And then 2, 1 above and below each of the other carbons in the middle chain, or in the middle of the chain. Okay, like this. And then chloroethene, C here. H2, C double bond, CHCl. So I'm going to draw actually the structural formula first. C double bond, C. One side just has 2 hydrogens. You can draw them at an angle like this to represent its sp2 trigonal planar shape geometry. The other side though has 1 H and another Cl in the other position. Okay, so that's the structural formula. How are we going to draw the skeletal formula? Well, remember, a point or a corner is one part of this chain. Then we'll have the other part. So just one line. We do need to indicate a double bond though, so you can just draw another line like that. We don't label any of the hydrogens, but we do label the heteroatom Cl like this. So you can just draw like this. All right. And then, sorry, this is not number 1 again. Number 2 will do. Number 2, which of the following has the same empirical formula and molecular formula? So, can any of these be divided? No. The first one has 1 carbon, it can't be divided anymore. The rest have 1 oxygen. So we don't need to worry. Those are all potentially empirical formulas. But is that empirical formula the same as the compound's molecular formula if it has a molecular weight of these numbers, 90, 62, 88, 72? So what you need to do is, even just roughly, calculate the molecular weight of those empirical formula. So right away I can see A is not possible for them to be the same because a carbon, 2 oxygens, and a hydrogen does not equal 90 mass, 90 atomic mass units. It's 12 plus 32 plus 1, that's about 45. That is in fact half of 90. So that means this empirical formula has a molecular formula that is double. So this actually would be C2O4H2. So this is not the same. How about CH3O? You can do some quick math there. Carbon's about 12, hydrogen's about 1, 3 of those, plus 16, 31. Same problem here. Instead of having a mass of 62, this has a mass of 31, so it would be doubled. C2H6O2. So it can't be B. C, C2H8O. Quick math on that. 12 times 2 plus 8 plus 16 is 48. So can't be that. How about D? 12 for carbon times 4 plus 8 plus 16. that is in fact 72. That means this compound's molecular mass matches its empirical formula, and that means its molecular formula is also the same as its empirical formula. Okay, so it's probably been a while since you've done empirical and molecular formulas, but they do show up again here in organic chemistry quite a bit. I do actually just want to talk about one more slide here. So oftentimes you'll hear people talk about man-made versus natural chemicals and how some are safe and some are toxic. So I kind of made this infographic with Google Gemini. So if you really look at some of the details in these pictures, it might not make sense, but I think the overall points are good. So we can have synthetic things that are very toxic, or things that are man-made and synthetic that are made in a laboratory that are quite safe, at least as safe as natural products. You can also have very toxic natural products and also safe natural products. Okay, so things can be categorized into these 4 categories. But again, I will say everything depends on the dose, right? Anything is toxic if you take too much of it, and anything can be harmless if you just have like a couple atoms or molecules enter your body. But I think what I'm talking about here is similar amounts of these things, maybe like a couple milligrams or 1 milligram. If we use that as a baseline, there's definitely some very toxic things and some quite safe things. So just synthetic toxic things, we might look at paraquat, herbicides, pesticides, synthetic drugs like fentanyl. Obviously people do that recreationally, but even a couple of milligrams will kill you, I'm pretty sure, of fentanyl. These are potent and high risk, and there's many synthetic toxic chemicals. Natural toxic then, just as bad. We can have alkaloids like strychnine, I think from some plants, toxic plants and mushrooms. Ricin, if you ever watched Breaking Bad, you know that's in some beans and can be used to kill people, or people eat it by accident and die. Defense mechanisms from plants or animals like, poison dart tree frogs, fungal toxins, aflatoxin. There's many. There's tetrodotoxin from pufferfish in the ocean. Some of the most toxic chemicals, even very, very low doses, can injure or kill people. Then synthetic safe things, aspirin. It's a good anti-inflammatory drug, although it is toxic even in very small amounts to babies and infants, so we don't give it to babies. So age of the subject is even a consideration for whether this is toxic or safe or not. Other prescription drugs are generally safe, antibiotics, and very useful. Food preservatives, although I'd still say avoid food preservatives as much as possible. It's better just to eat food without them, although overall they have been a good thing, I think, for keeping our food shelf lives sort of stable and reducing waste. Then natural safe products as well, obviously, things like glucose, we have to eat every day for energy. Vitamin C, it's very hard to overdose on vitamin C. I'm sure you can drink several cups of orange juice and get thousands of percent times your recommended daily amount, but it doesn't really matter. It just goes in your body. Some of it's used for energy, some of it's secreted in urine. Other things like amino acids we need for building proteins, so we eat meat or nuts or eggs or whatever. We need those as well. So these are just some examples of different areas on the spectrum of synthetic and man-made versus natural, and safe versus toxic. But again, everything depends on dose. So take what I'm saying with a grain of salt. All right, so next time we'll go on to functional groups. Hope you enjoyed and learned something today. That's all. See you next time.